In this lesson, we're going to learn how to build a confidence interval for means. Remember that the goal of a confidence interval is to use a selected sample, it need to be a random sample, to capture a true population parameter, which in this case is going to be mu. So we're going to look at the case when sigma is unknown. We talked in class how the case where sigma is known is so incredibly rare. So when sigma is unknown, we saw that our z-critical value just didn't do a very good job estimating the confidence level that we needed. So we use the t-distribution, and the t-distribution is similar to the normal curve, except that there are many t-distributions, and that's based on the degrees of freedom. The t-distribution, well, the greater the degrees of freedom, the narrower or the less area will be in the tails and the higher the peak will be. So you notice that this purple curve here is the normal model. So the higher the degrees of freedom, the more it begins to look like our normal distribution. So we've talked how the degrees of freedom is 1 less than our sample size, n minus 1. So let's now look at some of the key aspects of a confidence interval. So when we build a confidence interval for means, we are going to use our point estimate, which will be x bar, plus or minus our margin of error. And our margin of error is going to now use a t star because we're going to be using the t-distribution times the standard error of the statistic. This procedure that we're doing is known as a one-sample t-interval for means. So now we're going to use table B to find our critical t-value. And then we'll do it a second time using t-star on the calculator. So we're supposed to first of all build a 96% confidence interval based on a random sample of 22 observations. So we're going to need our degrees of freedom in order to find our t-star, our critical t. So this would be equal to 22 minus 1 or 21 degrees of freedom. So it's finally time where we get to use table B in this course. So I encourage you to pull out your formula sheet so you can finally see table B and observe how it is set up. So across the top you have your degrees, along the columns you have your degrees of freedom. And here is the area in the tails. Specifically, it would be the area in the upper tail if you're looking at this diagram here. So in our scenario, we want 21 degrees of freedom and 96% confidence level. So at the bottom is your confidence level. So here's 96, and we're going to go up to 21. So that is this value right here, 2.189. I want you to observe something else. Notice that as the degrees of freedom get bigger and bigger, eventually as we approach infinity, these values here should look familiar to you. We said that as the degrees of freedom approach infinity, it becomes more and more normal. Well, with infinite degrees of freedom, it's the same as your normal distribution. So look, for a 95% confidence level, 1.96, that's the same as your z-star, your z-critical values. So if you wanted to, you could actually use your table B to get your critical z values. So our degrees of freedom was 21, and our critical t, or t-star, is equal to 2.189. And you should notice that this is bigger than a 96% confidence level z-star when we're using our standard normal for proportions. And it has to be bigger because we need to capture the true proportion, so it's going to create a larger interval. I'm just going to talk you through how to do this on your calculator, as my app is not presently working. So it's in the same place as inverse norm. You're going to hit second vars for your distributions, and it's option 4, and it's listed as inverse t, it's capital T, and it's going to ask you for both your area and your degrees of freedom. And now for your area, if we're doing a 96% confidence level, what this calculator is doing is it's actually giving your cumulative frequency beginning on the left. So you've got to think about what area is left over in your tails. So if you have 96% confidence level, that's 4% left over, that's 2% in each tail. So if I enter 0.02 for my area and then my degrees of freedom, 21, it's going to give me my negative T-star value. It gives me negative 2.189. So when you go to use it in your confidence interval formula, just switch it to positive. The other alternative, if you actually wanted that positive, is since it's giving you your cumulative, you could put in 98% because that would then add this tail here and then this 96% till you get to here. But I think it's just easier to recognize, put in this left tail and you get then the negative T critical value and just switch it. All right, so let's look at a 99% confidence interval from a simple random sample of 71 observations. So that means our degrees of freedom would be 70. So let's look at how to use our table here. So you'll notice that the degrees of freedom jump from 60 to 80 in your table. So you're going to round down, you're going to use 60. And what this will do is it'll give you a margin of error that's a little bit bigger than if we use the technology. So we'll expect our T-star to be a little bit bigger this way, but we're going to do 60 degrees of freedom and a 99% confidence interval. So I'm going to actually zoom in here. So 99% confidence interval, we're going to be using 2.660. We get 2.660. Okay, so let's quickly just do it from technology. We're going to be using inverse T, so you hit second bars. Now if we're doing a 99% confidence interval, that means we have 1% left out, so that's 0.5% or 0.005 in each tail. So I'm just again going to get my left, I'm going to put my left area in of the left tail. Degrees of freedom is 71. And when I do that, I get negative, but I'm going to switch it to positive, 2.647. So you see that this T critical value is a little bit smaller, and that's because we didn't need to round down our degrees of freedom to 60. So which are you going to use? Probably the technology. It's giving you more accurate answers, but occasionally, you might question whether or not you're operating the calculator right, especially on the exam. Do a quick glance at table B and make sure you're getting the same values. Before we go into a complete confidence interval problem, let's just do a refresher of what our conditions are for sampling distributions for means. So our first condition, of course, is we must have a random sample selected. And why is this? It's so we can generalize our results to our population. We need to check our 10% condition, meaning that our sample size must be less than 10% of the population. And that's so that when we're sampling from a finite population, that sampling without replacement is okay and independence is not violated. And then we need to check our large counts, also sometimes called your normality condition. And there's kind of three parts we need to look at. And the first would be if we know that our population is normal, the size of our sample doesn't matter. Okay, we can assume that our sample is also normally distributed. However, if we don't know that, then we have to consider the size of our sample. If our sample is large enough, and we use 30 as our cutoff, so a sample of 30 or more, we saw that by the central limit theorem, the sampling distribution of X bar will be approximately normal, so it's going to be okay to proceed. But then we're going to look more closely in our next lesson on, well, what do we do when our sample size is small, when it's smaller than 30? And we use this notion that we proceed if our sample data does not show strong skewness or outliers. And again, why do we even check our large counts? condition, and that's so our sampling distribution of our sample means will be approximately normal. Okay, so now we're going to go through a scenario where we actually construct our confidence interval to capture a true mean. So it says Reese believes the students in her large high school spend way too much time on their phones and other devices. To investigate, she estimates the mean amount of daily screen time for all students in her school by taking a random sample of 50 students. She finds the average daily screen time for the members of the sample is x bar equals 7.1 hours with a standard deviation of 2.4 hours. We are to construct and interpret a 90% confidence interval for the mean amount of daily screen time for all students in this school. So as always, we're going to follow a state plan do conclude model so that we don't miss any important points. So I've stated that I want to construct a 90% confidence interval to capture the true mean time in hours, making sure I'm talking about my population now, spent on all devices by students in Reese's large high school. Now as we go on to do, let me refresh you of our conditions for means that we talked about when we looked at sampling distributions for means. So if conditions are met, I will construct a one sample t interval for means. I often write for mu, so it's really clear that I'm capturing my population parameter. So let's check these conditions. So the first is random, and I always put it into context of the problem. So a random sample of 50 students was selected. Next would be our 10% condition. And I state that 50 students is less than 10% of all students in the high school. Lastly, my normality condition, I say normal or my large sample. The sample size is large, n equals 50 is definitely greater than or equal to 30. So my conditions are met. And now let's go on to our do. So in my do, I need to be sure that I am doing several things. The first would be I'm going to need my general formula. So I like to write this down that I'm going to be doing x bar plus or minus my t star times the standard error of the statistic. So as I do this, I'm going to need to make sure I have my degrees of freedom labeled, which is going to be 49 because it's n minus 1. I'm going to need my t star value. So you're either going to use table B, but however, I think most of you are probably going to be using your technology. So we're going to write inverse t. It's important that you label what these things are. So if it's a 90% confidence interval, again, that's 10% left out, so that's 5% on either tail. So I want the tail. This will give me the left one, and my degrees of freedom of 49. So my t star by my calculator is 1.677. So now I'm just going to substitute that my confidence interval now would be equal to 7.1 plus or minus my t star 1.677 times the standard deviation of my sample. 2.4 hours was given in the problem, divided by the square root of my sample size, which was 50. So when I do this in the calculator, I get an interval of 6.53 to 7.67 would be the hours that our true mean falls in. So it's just time to interpret. So let me shrink this to give some space. So I've stated that I'm 90% confident that the interval from 6.53 hours, notice I'm putting units on this, to 7.67 hours captures mu, make that look like mu, the true mean number of hours that students in this large high school spend on their devices. Lastly, it says a recent report stated that U.S. teens have 6.7 hours of daily screen time on average. Does the interval from Part A provide convincing evidence that the mean at Reese's school differs from the national average? I've stated that no, because 6.7 hours is in the confidence interval, it is a plausible value for the mean amount of daily screen time.